I'm so glad you're here for another episode of Mechanism Monday, where every Monday we write out the electron-pushing arrow mechanisms for different organic reactions. In last week's video, I asked if you could solve the mechanism for this organic reaction, so if you haven't had a chance, pause the video now and try it independently. And make sure you stick around to the end because I'll give you another mechanism to solve for next week's video. This is a really unique reaction that comes to us from Batt and co-workers in the Journal of Organic Chemistry, published in 1992. You can check out the reference right here. And uniquely, you'll see that we're forming this fused ring system. And anytime I see a ring formation, I'm often going to be looking for cycloaddition reactions, which are why Diels-Alder type reactions and other cycloadditions are so powerful because they allow us to form different types of rings in organic chemistry. But this reaction actually begins with a Michael addition, where the first step of the reaction is that the nucleophilic oxygen of the alcohol can actually attack the 4 position, or this carbon in particular, and actually kick up these pi electrons. And in this conjugate addition, this will also kick up these pi electrons to give us a negatively charged oxygen. And this is actually going to form an enolate species. So the product of this first reaction is going to be this enolate, where we have the negatively charged oxygen that is adjacent to this pi bond, and that's what's known as an enolate. And then the rest of our molecule still looks mostly the same, except for now, remember, we have this positively charged oxygen where that alcohol came and attacked. And then we still have our alkyne located here. And actually, let me redraw that, because remember, alkynes are sp hybridized, which means that they have bond angles of 180 degrees. For anyone out there, typically we draw these as being linear. And the next step in this reaction is just going to be a series of proton transfers. Following tautomerization, we can now do an ene reaction, where those pi electrons in the carbon-carbon triple bond can actually do a reaction where it's abstracting a hydrogen. And from here, remember, we had excess amount of this alkyne with the alcohol on it. And that second or additional alkyne can come in and react as a nucleophilic attack on our aldehyde, following the formation of that 5-membered ring. Next, we undergo another series of proton transfers. And then finally, the electron lone pair on the alcohol can come down, and that's actually going to allow us to shift over our pi electrons to generate a new enolate species. And following a subsequent proton transfer, that's how we generate our final product. If you enjoyed this week's mechanism, give it a thumbs up down below. And for next week, I'd love to see if you could figure out the electron-pushing arrow mechanism for this organic reaction. Drop your thoughts as a comment down below, and make sure that you subscribe to the channel so that you never miss out on another Mechanism Monday. I'll see you next year.